Hello everyone, my name is Li-Hsing. I'm a professor at the Department of Computer Science, National Yangming Jiaotong University. Today my topic is DRL-based distributed joint serving and charging scheduling for UAV swarm. Here is the outline of my presentation. First, introduction. And in this paper, we use UAVs as flying base stations that provide access service to targets like user equipment or sensor nodes. But due to the energy constraint of the UAV needs to fly back to charging stations for charging. So now if we have a fleet of UAVs and we have some targets with known locations and populations, then we consider how to that each UAV autonomously determine its mission. That is, whether it should serve or charge at a particular moment. And we do this without the need of inter-UAV communication. We model this problem as a multi-agent Markov decision process. And we used deep reinforcement learning, or DRL, with partial observation for this problem. And we will report on simulation results. Okay, some related work. Some scholars attempt to that each UAV moves towards some location where the aggregated signal to interference ratio experienced by all targets, okay, that are associated with this UAV is maximized. And the problem of this research is that actually UAV cannot receive the information of SIR that is measured at targets. So later on, some researchers proposed a game theoretic approach that minimized the distance from UAV to each associated target. Okay, but these two studies did not consider charging issue. We do have many centralized charging and serving scheduling studies. However, these studies are centralized. And a previous work also proposed a game theoretical approach that maximizes rechargeable UAVs service coverage. We share the same problem setting and goal with this approach, but we do not use a game-based solution. Here is our system model. The target area is divided into multiple sub-areas. Okay. Within each sub-area, we can see a number. These numbers represent the coverage demands of these sub-areas. For example, if the number is 3, that means we need 3 UAVs to cover this sub-area. And the coverage of each UAV is the sub-area where the UAV resides and all the surrounding sub-areas like this. And we may have multiple UAVs that overlap their coverage, so that, for example, in this sub-area, both UAVs serve this sub-area, so that the coverage demand of this sub-area can be met. However, UAV has limited battery, so regularly these UAVs should recharge their battery. So we assume some sub-areas like these three has charging station. In a charging station, we have one or more charging slots, one for each UAV. And there are three operation modes for UAV: serving, moving, standby, and charging. Corresponding to these modes, a UAV has 4 possible actions like charge, serve, fly, or rest. And we divide the time into time slots. So this is an example of scheduling of a UAV at T time 0, the UAV could fly, and at this time the UAV arrives at some sub area to serve targets, serve. Then when the battery power is low, the UAV start to fly back to a charging station for charging. Okay, after his battery power is full, the UAV turns to fly to another target. Okay, the objective of each UAV could be formulated like this. Suppose we use DA sub A to be the coverage demand of a sub-area A. Then the service coverage intensity of this area A will be DA, like 3 or 2. Okay, if 3 or 2 or more UAVs actually covered this sub-area. Okay, if the number of UAVs that cover this sub-area does not equal to or exceed DA, then the service coverage intensity is 0. The goal of each UAV is to maximize the accumulated service coverage intensity, which could be formulated like this. Okay, here we have several indicators. This one is if the UAVP is charged in time t, and this indicates whether the UAV is serving in time t, and this indicates whether the UAV is flying in time t. Okay, actually these three variables, these three indicators cannot be 1 at the same time. Only one of them should be 1. Okay, another indicator here is if UAVP resides in sub-area A in time t. Okay, so we have to decide the values of these indicators such that the service coverage intensity in sub-area A in time slot t, we take the sum of this for all time slots and all sub-areas. So these here we can see constraints of our objective. We have to meet the condition that each UAV can reside at the most one sub-area at any time. The number of charging slots is limited in each charging station, and we must not drain our battery power during serving and flying. And UAV can only be in one out of 4 operating modes. UAV can only charge in the sub-area with charging station, and the UAV can rest in the sub-area without charging station. And this is the speed limit. Okay, we model this problem as a Markov decision process. If we are concerned with a single UAV, it's a single agent Markov decision process, or MDP. Of course, the agent is the UAV. Possible actions are fly, serve, charge, and the rest. state of the UAV includes residual energy of the UAV, observable targets, and charging stations. And we also assume that the UAVs have limited visibility, so the MDP is of partial observability. But we have a fleet of UAVs, so actually the problem is multi-agent, partially observable MDP. We use DRL to design the distributed mission and the charging scheduling for rechargeable UAVs. We take the paradigms of centralized training with decentralized execution. That means all UAVs collaboratively train a common learning model offline, which is then used by each UAV to independently make online decisions in execution time. And we use two learning models. The first one is double deep queue network. The second one is deep recurrent queue network. In this model, we replaced FC2 layer with long short-term memory, LSTM. About the simulation, here we can see the simulation setting about the environment, UAVs, and the training models. First, we change the number of UAVs and also the charging rate. Here we can see as the number of UAVs increased, the coverage ratio also increased in general. For game-based solution, the previous work, the coverage ratio increased when the number of UAVs is less than 20. However, when more than 20 UAVs are involved, the coverage ratio tends to decline a little bit, does not increase anymore. Okay, quite odd. But for DRQN and DDQN, we always have the trend of increasing coverage ratio when the number of UAVs are increased. And we also see how the average residual energy, okay, in percentage changes when we change the number of UAVs. Okay, here we can see the game-based approach will change the increase the residual energy when the number of UAVs are increased. Okay. However, for the DRL-based approach, the ratio remains the same when we increase the number of UAVs. We also conduct a cluster distribution of service demands like this. Okay. And the results are similar to the previous case. Okay, we also change the charging rate and the number of charging slots when the charging rate is 0.5, 1.0, and 2.0. And also when the number of charging slots are 3, 6, or 9. Okay, here we can see the coverage ratio. The conclusion is when the charging rate is high and we have more charging slots, the DRL-based approach can approach the performance of the game-based approach. Okay, and here the results are similar. So conclusions. We have proposed the distributed serving and charging scheduling for a UAV swarm to maximize service coverage intensity. We model the problem as a POMDP and proposed two DRL-based approaches. The proposed approaches can handle distributed serving and charging scheduling as long as enough charging facility is provided.